Hi, my name is Sergey, and today I will tell you about our library for machine learning enhanced seismic interpretation. It consists of methods for loading amplitude cubes and labels, training and predicting with neural networks, as well as quality control functions and visualizations. All of this is highly optimized and tested on dozens of actively developing fields. So let's dig in. First and foremost, we must be able to infer information about seismic cubes. They are usually stored in segue format and use a different subset of headers for indexing. We hide all this complexity behind just two parameters: which headers to analyze and which of them to use as indexers. This way we can work with both pre-stack and post-stack geometries. At loading, we opt to take extra time to carefully analyze value distributions and other properties of a cube. This is done only once for each field and stored right next to the data for later loads. Displaying the instance shows several important attributes, and we usually use it for quick introspection. For example, we can see the area of a field and its shape. During the model training, we repeatedly show an example of input and desired output data to a neural network. That requires high loading speed, and that is not something Segway provides. We would also like to reduce the disk usage, as some of the fields can take up to a quarter of a terabyte of space. We have developed two lossless formats for storing seismic data with these goals in mind: loading speed and storage efficiency. They are based on well-known scientific storages HDF5 and BLOSK. Under the hood, we leverage the rigid structure of post-stack data cubes, as well as modern compression. We also have two lossy data storages that contain quantized amplitude values. That allows to drastically reduce memory footprint with little to no loss in information. The conversion process takes just a few minutes and can be run by executing the convert method. In the end, we can see that the size of the optimized storage is 4 times lower than the original one. On each field described by SeismiQB, there are a lot of other entities. Currently, we can work with horizons, which are two-dimensional surfaces, flat faces, folds, and geobodies. We have tons of methods for each of them. For example, for a horizon we can remove spikes, smooth out the remaining values, and interpolate all missing points. In data science, it's crucial to look at your data before doing any fancy modeling. We have dedicated graphs to display slices along the chosen axis. Also, we can show attributes along surfaces, which is essential for facial location. Moreover, we have an interactive viewer for express assessment of a field, as well as fully fledged three-dimensional plot. All these functions are part of our library, so it is convenient to use them for exploration. The main purpose of our library is to develop and release in production machine learning models. We borrow a lot of training and inference methods from our parent library Batchflow. For example, a relatively complex model composed of multiple ResNet-like blocks can be configured with a short dictionary. Another feature allows us to generate data for model training in multiple threads, eliminating the CPU delay. We will tell you more about Batchflow in a separate course. For now, let's look at the template pipeline of model training. We use a very similar one to detect horizons, faces, and folds. The pipeline is a plan of actions to perform, and it is easy to read and understand even for people with no programming background. In the first block, we generate locations of a field to train on, then load seismic data and corresponding segmentation masks, and apply normalizations. In the second block, we use augmentations to increase the dataset size, and finally, we use images and masks to train a model on. This whole process is repeated for a number of iterations until the training is converged. The inference pipeline looks pretty much the same. The only noticeable difference is in the absence of test time augmentations, and we use a model to predict, not to train. Our easy-to-follow and understand pipelines help us to both research different training approaches and present them in a comprehensible way. While working with huge fields, which are described by 100 plus gigabytes of raw amplitudes, we want to be very careful with memory management. To this end, we do most of the processing tasks sequentially and work with data in chunks. On the other hand, we want to compute everything as fast as possible, so we use our GPUs not only for model training, but also for the most demanding computations. Inside our library, there is a separate module with optimized functions that automatically choose an available device to use. For example, geological attributes and metrics are all evaluated on GPU, taking less than a second instead of multiple minutes on CPU. Today you learned about our library for seismic interpretation with machine learning. It can work with multiple seismic formats of cubes and labels, train models on them in a highly optimized way, and control the quality of labeled entities. The library is completely open sourced on GitHub, so you can easily test it on your own data. Feel free to ask any questions regarding the usage of SeismiQB on our page, and we will be glad to help.